So in order to talk about physical properties of soils, I would like to first make sure everybody is on the same page with some definitions of physics. So I will start with weight, which is mass times gravity. So I'm going to be using capital W for weight, capital M for mass, times gravity. The unit weight, I'm going to use gamma for unit weight. Unit weight is weight of unit volume of an object. So this is the unit weight. And the density, more correctly, mass density, is mass per unit volume. So weight is the gravitational attraction on your object, and mass is the amount of matter in your object. So this is your density. And then specific gravity is unit weight of your object divided by or normalized by unit weight of water. Which also means density divided by density of water, because this is the unit weight is density times gravitational acceleration due to what we have written above. So these are in common language. These might be used interchangeably. So it's important in this lecture to correctly distinguish between them. When we are talking about the soil, the totality of the soil, we usually use unit weights and densities, but when we talk about the solids, the minerals of the soil, for some generally accepted convention, what we use is the specific gravity then. So let's write it this way. So here I also have used a little subscript W. So I'm going to be using little w for water phase, little s for solids, little a for air, v for voids, which is air plus water, or total soil minus solids. And then I'm going to use T for total soil. So here, this is a little important detail that people often get confused. I'm not going to be using S for soil. S is going to be always for solids in this lecture. So, then if we consider the phases in a body of soil, what you have is you have a gas phase, which is air. You have or you may or may not have a gas phase. You have a liquid phase and you have a solid phase. So usually what we do is we put these into a phase diagram. That is something that looks like this. And then you can write masses. So mass of air is going to be, for engineering purposes, 0. You can have mass of water. You can have mass of solid. And the air total is going to be your mass total. And you can also do this with weights, obviously, weight of water, weight of solids, etc. But weights are rarely used in these phase relations. And you can also write things in terms of volumes. So you can have volume of air, volume of water, volume of solids. And these two make volume of voids. And these three make volume total. So I just put the convention we learned on the previous page, I put that into use here. Now, yeah, these are fine by themselves, but these all depend on the amount of soil you have. So what would really characterize soils better is the proportions of these phases. So for that purpose, we have a bunch of ratios, a bunch of parameters that are ratios that we very frequently use. One of them is the water content. The water content, and when I say water content, I by default, I'm going to be meaning mass or gravimetric water content. Mass or gravimetric. So what is this? I'm going to be using a lowercase w for it. And it is mass of water, ratio of mass of water to mass of solids. So it's a little counterintuitive because it is not the fraction of the whole, it is just proportion between water and solids. And it is very commonly expressed in percentage. So if you are going to do that, you need to multiply this with 100%, obviously. Now, there's also an alternate parameter to this. So that is volumetric water content. But I'm going to put this in parentheses because I'm a geotechnical engineer, and in civil engineering, geotechnical engineering, or in soil mechanics, this is rarely used compared to the mass water content. That's because determining masses or weights is much easier than determining volumes in soil. So, however, other disciplines often use this. Environmental engineers, agricultural engineers, they use this volumetric water content a lot. So let's have that here as well. And this one is differently defined from the mass water content because it is volume of water over volume total this time. But as I said, you don't have to remember this one for this course, but for your future career, it is something to remember. Now, other ratios are degree of saturation. We are going to use a capital S for that. And degree of saturation is, now this, the first one was how much water you have relative to the solids. The second one is how much water you have in your voids. So what fraction of your voids is filled with water? And that is expressed as volume of water over volume of voids. And then the third one is void ratio. It is expressed with, it is denoted by lowercase e, and we will use it very frequently. And it is the volume of voids divided by volume of solids. So again, it is quite counterintuitive because it's not relation to total. And once again, there is an alternate version of it, and that is called porosity. But actually, this time I'm not going to put it in parentheses. You need to know porosity as well because we frequently use both. And once again, the void ratio is used only by geotechnical engineers, and porosity is used more widely over other disciplines. So this one is volume of voids over volume total. So what fraction of your total volume is voids in porosity, whereas here it is the amount of voids per unit volume of solids. And because these are very similarly defined, you can very easily relate one to the other. Basically, you don't have to memorize these things. Actually, let me put this up in front. In this chapter, between these relationships, you can come up with a lot of equations, a lot of relations between these parameters. And if you look at any soil mechanics book, you are going to see a lot of such relations, a lot of equations, a lot of formulas. But I have never memorized any of those, and I still don't know them, because just by thinking about the physical definitions of them, you can very easily write them down, very easily deduce them. So I'm going to show you a couple of examples now. So for example, we defined porosity as amount of or volume of voids per total volume of the soil. So if the total volume of the soil were 1, then how would you define the void ratio? If the total volume was 1, the amount of your pores would be n, the volume of your pores would be n, and the volume of your solids would be 1 minus n. Similarly, if I didn't think about that, if I were trying to write n in terms of E, if my volume of solids were 1, then my volume of voids would be E. So I could write this. See, it is very dangerous to memorize these because they look alike and you can very easily get confused which one was minus, which one was plus. Don't ever memorize this. Okay, it's always better to figure out by actually selecting the denominator as 1 in one of the parameters. So for example, for this one, for the porosity, what I did was I selected the volume of solids as 1 and then volume of voids becomes E, and then I could easily write the total volume is 1 plus E. So please don't memorize anything in this course. Okay, so basically these four definitions are relatively important. You have to know these four. You have to know these four. Okay. Plus we have a few more. Let's list them as well. The others are actually based on what we have talked about so far, such as unit weight. For example, you can have unit weight of soil. What would be the unit weight of soil? What is unit weight? Unit weight is weight per volume. So this will be the weight of soil, total weight over total volume. And once again, this is not something new because you already know the definition of the unit weight. But then we have a few more types of unit weights defined here. So let me also go over those. So yes, this is the unit weight, and we very commonly, in order to distinguish this from other unit weights, we very commonly call it the bulk unit weight. Then we have a pair of other unit weights. These are dry unit weights. What is this? It is not the unit weight of the soil if you dried it. It is rather the unit weight of the soil preserving its structure, its volume, in the absence of water. So it is like a hypothetical scenario. So it is basically gamma dry is equal to, if it is dry, then your total weight is just weight of solids divided by total volume. And then the other one is saturated unit weight. We show it with gamma sat, and that is weight of solids plus weight of water that fills all voids. Now I have to write it like that because the bulk unit weight, this volume total, is also weight of solids plus weight of water. Yeah, it is, but this volume of water is the actual amount of water in your soil. This is what if all the air space in your soil was also filled with water. So it's a bit different. And it will be always larger. So over total volume. Now, these two are hypothetical because changing water content can cause changes in the total volume of the soil. So basically, if you have certain types of soils, if you change their water content, they can, if you add water, they can expand. If you remove water, they can shrink. There are soils like that. So that's why I am putting this note here. But at this stage, we are in chapter 1 yet. We haven't started looking into deformations. So here, to make your thought process simpler, you can think of them as, yes, it is the dried form of the soil and the other is the saturated form of the soil. But that simplification will have to go away very soon. And when you consider these, it's always gamma dry and gamma saturated have to bound any possible value of the bulk unit weight, because with that solid structure, the lightest the soil can possibly be would be in its dry form, and the heaviest it can possibly be would be in its saturated form. So it's always like this. And actually, where you are in this range is simply going to be your degree of saturation. Now, so here, if S is 0, then gamma bulk is gamma dry. If S is 1, then it is fully saturated. And then gamma bulk is gamma saturated. So there is one more unit weight that I would like to define, and that is it's called the submerged unit weight or buoyant unit weight, or sometimes shown with gamma B. What does that mean? That simply means what does it weigh in water. So what does any object in water weigh due to Archimedes' principle? Its unit weight effectively decreases by the unit weight of water. So, but if it is in water, if it is submerged completely in water, it is also going to be saturated. So these will be gamma saturated minus gamma water. Actually, let me put a tiny additional note here. If you use subscript n for water content, it is called the natural water content. So it is the value of the water content in its natural state out in the field. So it's just a very commonly used expression. That's why I need to add that here. Now, how much does a soil weigh? A soil weighs about basically I would, for most common values, I would probably put 12 to 22 kilonewtons per meter cube to give you an estimate, or if you convert into gram force per centimeter cube, it's 1.2 to 2.2. So, but for unit weight, what we use is SI units. So here it is kilonewtons per meter cube, and gamma water is 9.8 kilonewtons per meter cube, or for most problems, most engineers directly take 10 for it. So let's see what else do we have. This page was all about unit weights. What else do we have? Now, as I said before, if you define anything with unit weight, you can also define such things with density. So you can have dry density, you can have bulk density, etc. Yeah, these are used, but for some reason saturated density isn't used. So these can be used as well. Now, what else do we have? We also have specific gravity of solids. So as I said, subscript S is for solids. So G is specific gravity. So GS is specific gravity of solids. And that is going to be density of solids over density of water, which means it is the mass of solids over volume of solids times 1 over density of water. So this is the specific gravity solids. Other than these, there are other less common phase definitions involved. So there is the specific volume, which is 1 plus E. There is air content, which is volume of air over total volume. There is also specific surface area, which is particle surface area over particle volume or mass. It's expressed in two different ways. But anyway, these are, we are not going to use them at all in this course. Well, we are not going to use them as such, but exception is the specific volume 1 plus E, even though I'm not going to use them, even though I'm not going to say specific volume within the rest of the lecture, the reason this is given a name is because it appears in a lot of equations. The reason for that is simple. 1 plus E is the amount of the volume of your total soil per unit amount of solids. So that's why it is being used. Now, I'm going to add a couple of things here. Actually, let's move on to the next page. Actually, let me write here. Some things that will come up are Emax and which is the obviously the maximum void ratio, and E min, which is the minimum void ratio. So these are related to how loose or dense your soil can be. So for a given assembly of solid grains, you can compact them well. So this is your densest possible configuration. And you can kind of stack them on top of each other in a metastable way. And that will be loosest possible configuration of your soil. So it also these are also going to come up at some point. Now, well, actually, if you have those, just like degree of saturation shows you where you are. There's also there's also another ratio called relative density. And it is, we are going to show it with dr, and it is where is your current void ratio in Emax, Emin range. So for Emax, it is the loosest. So remember, this is loosest, and that is dr of 0, and this is densest, and that is dr of 1. So if we express that mathematically, we are looking at where we are in this range, Emax minus Emin, and I want it to be 0 when I'm at Emax. Again, if you want to express it in percentile form, you can add a percentage to it. So I say these things, but I expect you to mathematically be able to think about that. So when you see relative density of 60%, you should know that you are not going to write 60 here. You are going to write 0.6. So 0.6 is going to be 60%. Now, another detail is deformation, volumetric deformation. Is change in in total volume. So let's write this delta ET. But wait a minute, your solids, unless you take away some of your soil, your solids aren't going to change volume. So that's also, oops, sorry about that. Delta, yeah. It's also going to be equal to change in the void volume, because the solid volume is, as far as engineering calculations are concerned, it is going to be constant. Now, because solids are, they have very little compressibility. Yeah, if you apply a lot of force, you can compress them infinitesimally. But now you might think, wait a minute, the water is also practically incompressible. Why are we not considering that? Because water is able to flow out of the soil pores. So if the water flows out of the soil pores, you can compress the soil more. So basically, when we name something as soil, when we define the extent of soil, we are generally defining it in terms of the solid skeleton and all the fluids encompassed in that skeleton. So if some of the fluid flows out, then it is gone. It is no longer in my soil. But the solids are there. So this means if we are considering changes in void volume, I would be able to relate this to void ratio. But first, in engineering, when you talk about any deformation, again, you want to talk in terms of proportions. So you want to talk in terms of strains. So volumetric strain. Don't worry, we are going to have big deformation chapters later, but here this is just a definition. And you probably know this from your either strength of materials or material science classes. So volumetric strain is change in volume over initial volume. So what fraction of your initial volume has changed? And now here, my change in volume is change in void volume. So this is delta volume of voids divided by initial total volume in my terms. Now, if you consider for volume of solids of 1, this would make, if your volume of solids is 1, your volume of voids is E. So if your volume of voids is E, its change is delta E. And if your volume of solids is 1, your total volume is 1 plus E. I have a 0 there as well, so in the original state. So this is also a very useful relation to know. It will be used a lot in the deformation chapter, but here as well, you can use it for simpler problems without considering the engineering properties of the soil. So basically, here you can use it to figure out what that volume change corresponds to in terms of phase parameters. But later, we are going to talk about how or why that volume change occurs in the later chapters. So, as I said, this will come in handy in situations where the volume changes. So, okay, so let's solve an example to practice all of this. So we have a soil that has void ratio of 0.7 and specific gravity of solids is 2.7. So the question has a few parts. The first part is calculate gamma saturated, gamma dry, gamma submerged, gamma buoyant. The second part is if degree of saturation is 75%, calculate gamma bulk and water content. And part C, how much must the soil be reduced in volume to get to 90% saturation at the same water content. So let's start with part A. Now, in order to make sense of everything, in order to aid us to think in this problem, let's draw a phase diagram. You don't have to draw this, but I think it helps the thought process. So here I have my voids, here I have my solids, and the question says your void ratio is 0.7. So if I have, for volumes, if I have one volume here, I have volume of E over there. And if I look at masses for one volume here, I have a mass of volume times density. What's my density of solids? Density of solids is GS, which is, sorry, GS times raw solids. Sorry, GS times raw water. So for saturated, this volume, so for dry, this mass will be 0. For saturated, this mass, this voids will be filled with water. So it will be E times raw water. So if I sum these up, my total volume will be 1 plus E. My masses are going to be GS times rho W plus zero or E times rho W. 0 for dry, E times rho W for saturated. So from there, I can directly calculate gamma saturated is GS plus E times rho W over 1 plus E, and gamma dry is GS rho W over 1 plus E. Actually, I could have done this writing numbers, but the reason I didn't, the reason I worked this in parametric form is because I wanted to show you how to derive some equations. So you can assume something is 1 and then work your way around everything. So here, that's what I did. I assumed, and the most common is volume of solids. I assumed volume of solid is 1, and instead of writing 0.7 here, I wrote E, and then I obtained everything in terms of E. So if you wanted to work in porosities, for example, it would be better to assume total volume is 1. Anyway, so let's quickly calculate this. 2.7 plus 0.7 over 1 plus 0.7. Sorry. These are masses, so I need to calculate them in terms of weights. So let's make this weight, and these should be unit weights. Times 9.8. Now this is just, actually I don't need to calculate it for the calculator for this, because this side is just 2. So this is 19.6 kilonewtons per meter cube, which means gamma buoyant is 9.8 kilonewtons per meter cube, because this is the difference between saturated and water unit weight. And the other is 2.7 over 1.7 times 9.8. So that gives me that doesn't really matter. The numbers are unimportant. How to solve the problem is important. So that's basically it for part A. Let's see what we can figure out for part B. For part B, up here, I have 75% filled with water. So actually, let's move on to the next page here. So for part B, what I have is this time this picture: solid, water, air. And again, I'm going to put, for volumes, I'm going to put 1 here. And this would be E. But then I know that here I have S times E and 1 minus S times E as air volume and water volume. So then my weights become, again, GS gamma W here. And up here, this will be 0. This will be, it's water, therefore SE comma W. So then my bulk unit weight would be simply, my total volume is still 1 plus E. So my bulk unit weight is going to be GS plus SE over 1 plus E times gamma W. So if you calculate that, it's going to be 75% of the way between dry and saturated unit weights. So 2.7 plus 75 times 0.7. Divide that by 1.7. Multiply that by 9.8, and that is 1959 kilonewtons per meter cube. And my water content is easier. It is simply the ratio of these masses. So actually, if I write from these two, I write water content. My water content is going to be SE gamma water over GS gamma water, where gamma waters are cancelled. So SE over GS. So actually, this gives a very handy relationship. Actually, as I said, I don't memorize these equations, but this is so catchy that it kind of sticks to my mind. You have this relationship, which in many cases can provide you a quick shortcut. So that's basically, let's see what that gives. So that is 0.75 times 0.7 over 2.7. So that gives us 19.4%. Okay, let's see what we wrote for part C. How much must the volume be reduced to get degree of saturation of 90% at the same water content? And because we are in engineering terms, we are talking in terms of strains here. So, or maybe I should just rephrase the question. By what fraction, by what percentage must volume be reduced? So now I want to, it says preserve the water content, but reduce, preserve the water content, but increase degree of saturation. How is that possible? If I look at here, preserve the water content, I'm not changing specific gravity of solids either. If I want to increase the degree of saturation for the same water content, I need to reduce volume. I need to reduce voids. Or you can think of it in the phase diagram as well. If I keep this water content same, how am I going to increase the degree of saturation? I need to reduce air. So my task is then, how much am I going to reduce that? So I'll stick to the same values. If I had 75% of this E before, so I had Actually, this time I need to convert this to numbers because it's not just a standard thing anymore. So here I have 1, here I have 0.75 times 0.7 water, solid air, and here I have 0.25 times 0.7. So 0.75 times 0.7 is 0.525. And this is the remainder, 0.175. So now I want to convert this into something such that this 0.525 is 90% of my voids. 0.9 times E. So from there I can find my E is equal to 0.525 over 0.9, which would be something like that, 0.583 bar. So my old volume was 1.7 here. Now my new volume became 1.583. How much did it change? Well, you can either make a percentage of this, or I could just do it properly. Delta E over 1 plus E0. And that would be the difference between these two. 1.7 minus 1.583 over 1.7 was the original. So that would give me, or actually, you can even write 0 point. So that is about 7%, 6.9% decrease in volume. Of course, you need to pay attention if in the same problem you have decreases and increases of volume, which way is which. You need to decide one is plus, one is minus. You need to pay attention to that kind of things. But here we just have a decrease, so I just made the subtraction in such a way that it's going to be positive. Otherwise, actually, when I say delta E, change in E, this E is decreasing here, so it would have been minus. But as general convention, most of the deformations we have in soil mechanics are in compression. So actually, this is generally defined as compression is plus. So all of these would have a minus sign in front of them.